Hello, friend. My name is Derek Carter, and in our video today, we're going to be looking at the basic elements of a computing system. In particular, we're going to do a couple of examples using a very simple machine architecture definition to do some example problems. Okay, so we basically, the purpose of this video is we want you to understand how computers work at a fundamental level. So we're going to discuss the fetch execute cycle, some elements of how a basic computer architecture works. So this is kind of important stuff that computer science students need to kind of understand, computing's at this really high level, how they work. And the purpose of this video then is to try and give you an overview of that and look at some examples of how the fetch execute cycle works on a computing system. Okay, so if you're ready, let's go ahead and get started. All right, so first of all, let's just describe, most people think of a computing system as having four elements, okay? So the elements are the CPU, the central processing unit, or the processor, that controls the operation of the computer and performs data processing. Main memory, so the memory of the system over here is what stores the data and the code. So typically this is volatile, so this is often called RAM or primary memory or real memory, okay? I usually think of this as a big array. So if you're familiar with arrays in a language like Java or C, you can think of this as just a big array that's addressable, address 0, address 1, so on, up to the size of the memory. And each one of these buckets in a memory in a computing system holds the same amount of information, okay? So in modern computing systems, these buckets will hold 8 bits of information, okay? But in our hypothetical machine example we're going to look at today, we're going to be using the size of these memory buckets will be able to hold 16 bits, okay? But that's just part of the definition of the computing system and how main memory works, how big each one of these is, okay? So another important thing about memory, besides thinking of it as a randomly addressable array, is that these are what are known as stored program computers. So, we hold both instructions and data in our primary memory, okay? And how we interpret the bit patterns at any location in memory is going to be determined by the context of what we're doing. So if we're fetching something and we're expecting it to be an instruction, we will decode it and interpret it as a machine instruction. If we're fetching something else from memory and we are assuming that it's going to be like an unsigned integer, we will decode it and treat it like an unsigned integer. All right. So the bit patterns can mean different things depending on the context of what's in your main memory. All right. So besides our CPU and our main memory, a computer wouldn't be very useful if we didn't have some way of getting data in and out of it. So typically there are multiple I/O devices that are going to be attached to your computer. The whole purpose of those is as sources to either get data in or transmit data out of your computing system, okay? So I kind of think of as two different breakdowns. There are things that are communication devices, so your keyboard, your mouse, your network interface controllers are really about either moving data to and from you, the operator, or moving data to and from other computing systems, all right? But also, so since primary memory is volatile, we really need some sort of storage devices that are more permanent. Well, not permanent, but they can store data for longer periods of time. So another common I/O device are secondary storage devices like hard drives, right? And then a fourth component, you really need some sort of communication medium, some sort of interconnect for all these three pieces that we talked about to communicate, okay? So they have to be able to pass data back and forth from the CPU to main memory, from I/O devices into memory, from the CPU to I/O devices, right? So all those require communication. So that's the purpose of the system bus in the computing system. So at the most fundamental level, a computer is really doing this very simple, what's known as the fetch execute cycle here, okay? So instruction processing at the lowest level, the hardware level of computer, consists of a two-step process. So this process is called the instruction cycle. So in its simplest form, this is simplified a bit, but basically all the CPU is doing, the central processing unit, is it performs to process an instruction. Does these two simple steps. So processor first reads or fetches an instruction from memory. Okay, so this fetch is going to cause one instruction to be taken from primary memory and put into the CPU to be decoded. And then once it's fetched the instruction, that instruction will be decoded, interpreted, and executed. Okay, so it's relatively simple, and then we just keep doing that. Okay, so then after we fetch our first instruction and execute it, we'll go over and fetch the second instruction in our program. We'll fetch and execute it, then we'll go and get the third one, and so on. Okay, so these instructions, as you'll see in a moment, are very simple, right? So they're very simple, small operations. So the power of a computer comes from the ability to execute many of these instruction cycles, these fetch, execute instruction cycles, many of them in a small amount of time. So typically millions or billions of fetch, execute cycles happen every second in your computing system. Okay. So for the rest of this video, we're going to be working through a couple of example problems of how the fetch execute cycle works in practice on a simple computing system. Okay, so we're going to be using this definition of a hypothetical machine architecture from our textbook. Okay, so technically this is a 16-bit architecture because all of the instructions and all of the data are going to be held in 16 bits. Okay, so our memory, each word of memory is 16 bits long in this architecture. So technically that means that this is something like a 16-bit architecture, right? Like I said, for modern computers actually have kind of they've standardized on using 8 bits for every address in memory, but modern computers are actually 32-bit or 64-bit architectures. And that actually refers to the size of the address space rather more than the size of the buckets that you have in primary memory. Okay, but so for our hypothetical machine, each address in primary memory is 16 bits. The instruction format that we're going to be using for this hypothetical machine, we use the first 4 bits of each instruction that is fetched in is going to represent one machine operation that can be done. Okay, so it's going to represent the opcode, right? So since there's 4 bits, that means that there's a possibility of 2 to the power 4 or 16 different opcodes that we can implement. Okay, and here's some examples. So we might use the 4-bit 001 to be a load instruction, or we might use 0010, which is a hexadecimal 2, to be a store instruction, so on, right? And then the remaining bits for an instruction hold an operand. Okay, so so the opcode defines the operation to execute, and these remaining 12 bits are the second operand, which are going to be a memory address. So we'll use 12 bits to mean some location in memory that will work as one operand for instruction that the machine should execute, right? The other operand, so most instructions, like an add instruction, need 2 operands, right? So these are called 2 operand instructions. So if I want to add, I have to give it 2 numbers, like 3 plus 5, right? So for our opcodes, one of these operands comes from memory. So there'll be a specification of an address in memory that we fetch the value 5 that I'm drawing here. Will be one of the operands. The other operand will be in a register that we'll call the accumulator, or the AC, right? So the accumulator is always used as one of the operands, and this memory address, if we have an opcode that takes 2 operands, will be used for the other, right? And then the result of whatever the operation is, like the add in this case, so the result would be 8, that would get stored back into the accumulator as the result of executing this instruction. Okay. So to implement the fetch execute cycle, there's another special register that all computer architectures have called the program counter. So whatever the program counter is set to, that holds the next memory address for the fetch to happen. Okay, so the fetch has to happen before the execute that I was just talking about here. What happens during the fetch stage is the computer architecture looks at the program counter, reads the memory address in the PC, and then fetches that bit pattern, those bits at that memory address, into another register called the instruction register. Okay. Finally, on this slide, it's not enough just to have instructions. We have to have data that we want to operate on. Okay, so for this simple hypothetical machine, we're only going to have instructions that operate on signed integer data. Okay, so our signed integer operation that this machine architecture supports is a simple format called a signed magnitude format. So in this format, we've got 16 bits to represent data here. We'll use 1 bit for a signed bit. So if the signed bit is a 1, that means it's a negative number. And if the signed bit is a 0, so 1 for the most significant signed bit means a negative number, and a 0 means it's a positive number. Okay? And then the other 15 bits represent the magnitude. So if I want to represent, let's say, like a -1, I would have a 1 in my sign bit, and then all the other 15 bits would be 0. So that means for a -1, I have a 1. The next 3 bits would be 0. And then the next 4 bits would be 0. The next 4 bits would be 0. And then the next 4 bits would be 0, 0, 0, 1. Right? So that is actually -1. And if we represent that in hexadecimal, that ends up coming out as what? 8001. Right? So in particular, any signed integer that's a negative number is going to have a 1 in the signed bit. So it's going to be, so anything, when we look at these as hexadecimal that has an 8, 9, A, B, C, D, E, or F, is actually a negative number in our hypothetical machine. Okay? And so we could represent like a +1. So a +1 simply has a 0 in the signed bit, right? And then zeros for everything else except for the last bit for the magnitude, right? So in that case, the hexadecimal is just, so that's a 0 in the signed bit, so the hexadecimal is just 0001 for like a +1 here. So basically anything that's positive will have a 0 or 1, 2, 3, 4, 5, 6, 7 in the first hexadecimal digit when we're looking at these in hexadecimal. All right, so that's the basics of our hypothetical machine. So in a real computer architecture, of course, you would need much more than 4 bits because only having 16 different opcodes is a bit limiting. Another thing is in a real computing system, you'll have be able to support many other data types than just signed integers. You'll have unsigned integers, but you'll have floating point types, you'll have character types. So all those would have, you need to have different formats, if I want to do, and also different instructions if I want to do, let's say, floating point arithmetic. So for the rest of this video, I'm going to look through a couple of example problems of doing the fetch execute cycle by hand for this hypothetical machine that we just defined. Okay, so whenever you have a problem like this, it's really a very simple procedure. Okay, so it's just a automatic procedure that each individual steps. So as long as you do the steps one by one, it should be relatively simple to simulate doing the fetch execute cycle for a hypothetical machine. All right. So here I've added on the right hand side a couple of extra opcodes. Okay. So we've got 2 opcodes, and these are the binary. We've got 8 of our possible 16 in the hypothetical machine are defined here for these example problems I'm going to give. The first two are examples of memory access instructions. Okay, so if we have a hexadecimal 1 for the first digit, that means that we want to load a value from memory into the CPU. So load will load something from memory into the accumulator. And store does the opposite. So if we have a hexadecimal 2, we're going to take the value in the accumulator and store it back into primary memory somewhere. Right? The next three instructions are examples of data processing instructions. Okay, so these are the most typical kinds of instructions when you think of a machine instruction. So typically computers will have things for arithmetic like these: multiplication, adds, and subtracts. The other big type of data processing instructions are things like bitwise ands and ors, so logical operations or shifting bits, things like that. Okay, so here we're going to use hexadecimal 3 for multiplications, 4 for subtractions, and 5 for additions. Okay? And a third type of instruction. So these first ones are things for memory access. The second class of instructions are like data processing instructions. The third class of instructions are for basically changing the location of your program. Okay, so these are going to be like jumps or jump on 0 or jump on negative. So these change the flow of control of the computer as it's executed. Right. So as you see, so if you're used to programming in a high-level language, you don't have things like loops, while loops or for loops, or you don't have branch statements like ifs or else. So you actually have to use goto. So jumps are really just like gotos in a basic language. They say jump to a different location and start executing from that address in memory. All right. So let's look at this example here. So when you're first working on a problem like this, to do the fetch execute cycle by hand, the fetch stage should always be simple. The program counter tells you what is the location in memory where the next the next instruction should be fetched from. Okay, so whatever, in this case, our program counter is pointing to 2AA, right? So over here, I should maybe add this to our assignments, but these represent the memory addresses, and then the second column is what is the actual contents of memory, and everything on these problems are shown in hexadecimal. Okay, so in this case, all that ever happens on the fetch stage is whatever the program counter says, we take that value from the memory location 2AA in this case, and that gets fetched into what's known as the instruction register. So basically 48FF ends up here in our instruction register. That's all that ever happens on the fetch stage. The program counter says 2AA. I just copy the bits from memory address 2AA to the instruction register. All right. So now that I've got this bit pattern 48FF in my instruction register, I need to decode it. Okay, so you need to be able to convert from hex to binary. That's something I assume that you're comfortable with. But basically, each digit of a hexadecimal digit corresponds to 4 binary digits, right? And all we really need for these problems are, remember the first 4 bits of the 16 bits correspond to the opcode, right? So basically, the bits for the first 4 bits are really the bit pattern 0100. So this is actually a subtract instruction if I'm going to decode this, okay? So we're really doing a subtract, right? So really the execute stage is a little bit more complex than the simple treatment of our hypothetical machine. So what happens in the execute, after you fetch the instruction, you have to decode it. You have to also usually decode all of your operands. So usually for real computer architectures, you might have multiple operands. There might be different addressing modes and things like that. Okay, so we're doing a very simple sort of decoding here. We're decoding the opcode, which is a subtract in this case. And then the memory address are going to, the other 12 bits, the next 3 hexadecimal digits here represent the memory address, which is one of the 2 operands for the subtract, right? So to do this, for these problems, you should always have the accumulator as the first operand, right? So our accumulator has a value of hexadecimal 5, and be careful, you always need to be, aware that these are hexadecimal values. But I've got hexadecimal 5, and I'm gonna fetch the value from 8FF, which is hexadecimal 3, and subtract it. The result of that will be hexadecimal 2. Right? And then the result from these kinds of arithmetic operators, so the data processing operators, always gets stored back into the accumulator implicitly, right? So we'll end up with a hexadecimal 2 in our accumulator, right? Another thing that happens on the fetch execute stage, because the next fetch execute cycle, we want to fetch the next instruction in our program. So the program counter will be implicitly incremented if it doesn't get modified by something like a jump instruction. All right. So basically, we're going to always add 1 to the program counter after the fetch stage. So here, the program counter should change from 2AA to 2AB. Right? So that's the end of our first fetch execute instruction cycle for this problem. So for the next cycle, for the fetch, I've now got 2AB in my program counter. So I'll just fetch whatever's in 2AB into the instruction register. So that's a 33900 hex, right? And that's it. That's all that ever happens on the fetch stage. And then for our next execute, we need to first decode this instruction. So I've got a 3 and 900. So again, a 3 is like a multiply, right? So we know that we're doing a multiply. And the 1 operand for the multiply is going to be 900. All right. So we've currently got hexadecimal 2 in the accumulator. So this is saying take 2 times whatever's in address 9, which is 7. And the result of that would be 14 in decimal. In hexadecimal, that's what? A, B, C, D. So hexadecimal D. Because A is 10, B is 11, C is 12, D is 13, E is 14. Okay, so hexadecimal, I'll draw on that. So hexadecimal 14. I should put a hexadecimal to decimal table on this problem here as well. Right. So the result of doing the 2 times 17, which is 14, or E hexadecimal, would go into the accumulator. And don't forget to increment your program counter. So now our program counter should get incremented to 2AC in preparation for our next fetch execute cycle. Okay, so now we're on to our third cycle. So once I have 2AC, I'm going to fetch the contents of 2AC into the instruction register, which is 2900. And then we're going to decode 2900, which is a 2, which, according to our hypothetical machine, 2s are store instructions. All right. So we're not going to be doing a store. So in this case, we've currently got 0 hexadecimal E in the accumulator. Stores are memory transfer instructions. So basically whatever's in the accumulator is going to get stored out into the operand. So loads and stores only need one so the accumulator holds the value that's going to be transferred, and then the address portion of the instruction is the operand, which is going to be the destination of the store in this case. So basically we're going to overwrite the value in 7, and we're not going to have hexadecimal E stored out there. Right? And then don't forget your auto increment of the program counter. So our program counter is now 2AD. All right. And then here, our program counter is 2AD. So if you're doing these kinds of problems for my class assignments, you don't know what the value of 2AD is, right? So you're actually done at this point. So if we knew what the instruction was or what the bit pattern was at 280, I could continue on. I could fetch it and execute it. But I only had 3 instructions. We executed all of them, and we're at a part of memory past what we gave you for this problem. So that's it for the first problem. Okay, so let's do another one. Let's in this one we're going to throw in some jump instructions. Okay, so you can get an idea of how changing the flow of control of the program works. All right. So here, this one, oops. This one we meant to start at our program counter at 1FF. Okay, so let's start here. So the fetch stage should always be straightforward. 1FF means that we've got 47 AC will get transferred to the instruction register. And so that's it for the fetch. So then we will decode it. So a 4 is a subtract in our machine instruction architecture. Right? So subtract, you have to be careful for like subtract that you do the operations in the right order. So it should always be the accumulator minus the second operand that's fetched from memory. Okay, so in this case, we've got 2 hexadecimal in memory, and we're subtracting, we're going to fetch the value from memory 7AC and subtract that. So the result in this case is a 0. Okay, so we just end up with a 0 in the accumulator. Right? And our program counter should get incremented to 200. All right. So for our next fetch, our program counter is currently 200 or 200 hex. So we'll end up with 71FF in the instruction register. So when we decode 71FF, the 7 gets decoded as a jump on 0 instruction. Okay. So we're working on a jump 0 here. All right. Jump 0. All right. So in this case, what happens on flow of control instruction? So we had a 0 in the accumulator. So basically, in our hexadecimal machine, they make their decision. So the jump 0, the jump in are conditional jumps. They make the decision based on whatever the current contents of the accumulator are. So since the accumulator is 0, that means the jump is going to be performed, right? So here, the operand for a jump instruction is going to be what the program counter becomes if the jump is taken, right? So in this case, if the, we would do this in pseudocode as something like if the accumulator is 0, then change the program counter to be the address portion of my machine instruction register. So since it's 0, we're going to end up putting 1FF into the program. So again, so we're not going to go to 201 next. We're changing the flow of control of the program. We're going to jump back to 1FF and start executing from there, right? So it's a go-to statement. Okay. So for our next cycle, we've got 1FF now in our program counter. So we're going to fetch a 47AC. We did this instruction before. So the 4 is, just to remind you, is our subtract instruction. So we currently have 0 in the accumulator. When you do these problems for class, make certain you fill out all these. And for speed, I'm going through these and not always carrying these over as fast as I should. So since we have 0, we're going to be taking, again, be careful, the accumulator should be the left-hand operand, and then the value that we're fetching from memory, from 7AC in this case, is the right-hand operand. So the result of this one is going to be -2, right, hexadecimal. But again, remember the way our machine represents negative numbers. So in this case, we need to represent -2 as a 1 in the most significant bit because it's negative, and then zeros for the other 12 bits except for the last bits would be 0010. So that would be binary. But if you go back to hexadecimal for that, so that comes out as 8002 to represent -2 in this case. And then, don't forget your auto increment, so we increment back to 200 again. So we're going to try the jump Z again. So our next fetch, we're at address 200 hexadecimal, so we will fetch in the 71FF. We currently have a -2 in the accumulator. So we would decode the 71FF again as the jump on 0. In this case, though, we don't have a 0 value. So only if the accumulator is 0 will we do the jump. So since we don't do the jump, we'll just do the normal increment. Right? So the program counter now goes to 201. All right. So another thing for these problems for my class, you only have to do four complete fetch execute cycles. If we continued on, we would be fetching the address at 201, which is a store instruction. So the 2 is a store. So the result, if we did a fifth fetch execute cycle, should be that the -2 gets stored back out to the 7AB. But that would happen on the fifth fetch execute cycle. Okay, let's do another example. So in this one, we're starting with a program counter 1AB. So we'll get the 5941 in the instruction register. So if we decode 5941 on the execute stage, 5 is an add instruction. Form an add. And in this case, we've currently got 8003 in the accumulator, right? Remember that's -3 using our sign magnitude format for our machine. So we have -3 in the accumulator. To that, we're going to add in the value at 941, which is a +2. So the result of that is a -1, which in our machine representation should be encoded as hexadecimal 8001 in order to get the most significant bit as 1. And our program counter is going to get incremented to 1AC. Okay. So for our next fetch stage, our program counter currently says we're at 1AC. So we'll bring in the value from memory 1AC, 2940. Right? And we still have -1 in the accumulator. So we'll decode 2940. So the first 4 bits are a 2, which is a store instruction. So here we'll see an example of doing a store. So in this case, whatever's in the accumulator gets written out to the address that's the target of the operand. So we're going to overwrite whatever's in 940 with our -1 value. And we're going to increment the program counter to 1AD. Okay. So for the next fetch, we're going to get the value from 1AD, which is a 61AB. And then our next execute to decode 61AB. We have a 6, which is a jump. So this is an unconditional jump, right? So for an unconditional jump, it always happens. It doesn't matter what's in the accumulator. We just always perform the jump. So we've got an unconditional jump. So that means that so I've still got -1 in my accumulator. We're not going to increment the program counter. We're just going to change the program counter to 1AB, which was the operand for the jump instruction that we just did. All right. So that means that we're jumping back to the first instruction. We're going to keep executing that. Right? So remember, we're basically just going to keep adding 1 until we overflow So it's an infinite loop here since it's an unconditional jump. So for the final fetch that we'll do, we've got 1AB. So we'll get the 5941 add instruction back into our into the instruction register. So we've currently got -1 or 8001 in the program counter. So we have -1 should be the left-hand operand, and we want to get the +2 again. So we end up with a +1, which should be represented as 0001 in our hypothetical machine, right? And then we would increment the program counter to 1AC and continue on, right? So the next time we would fetch the store again, and we would end up storing 1 back over our value at 940 there. And then we would jump back and add 2 to it again, go up to 3. So it would go 1, 3, 5, 7, 9 after that. It kept going. Okay, so one more problem. So here we'll start at program counter 300 for our fetch. So we end up with a 1850 in the instruction register. If we decode the 1, it is a load instruction. So I'm going to perform a load here. So we'll get whatever's at address 850 and put that in the accumulator. Okay, so now we've got 00F. C in the accumulator, and the program counter gets auto incremented to 301. So for our next fetch, we'll look at the contents of 301, copy that in the instruction register, and then for our next execute, we'll decode the instruction register for 850. A 4 decodes to a subtract. This is a subtract. We currently have 00FC in the accumulator. So again, the order matters of your operand. The accumulator always comes first. These problems, we have positive FC, and we're going to subtract whatever's at 850. We're going to subtract FC. So the result of FC minus FC should just be 0. And our program counter will get incremented to 302. So for our third instruction cycle, we're fetching from 302, which gives us a 7301 in the instruction register. And then we're going to decode 7301. 7 is a jump on 0. Right. So in this case, our accumulator, this is a conditional jump. If the value in the accumulator is 0, we'll perform the jump, right? And so it is 0, so we're actually going to jump to 301 instead of auto incrementing to 303 in this case. All right. So for now, from 301, we're going to fetch the 4850 again into our instruction register. We'll decode our 4850, which is the subtract again. So, and again, in this case, we've got 0 in the accumulator this time. So we're going to have 0 subtracting the positive FC. So the result would be actually a negative FC, right? So I mean, we could convert this into binary, the bit pattern, but we know that basically the only thing that should happen is we've still got the same magnitude. We just need a 1 in the most significant bit. So the result of that is going to be that we end up with just an 8, have a 1 in the most significant bit, 0s in the next 3 bits, and then still have the FC for the last 8 bits in the accumulator. Right? And we're going to increment to 302. So if we could keep going in this case, the next time when we fetch from 302, again, that's the jump 0, but we don't have a 0 in the accumulator. So at that point, it would actually continue executing instructions at 303, since we don't have 0. All right, that's it for this video. I hope that that was helpful for you in understanding these kinds of problems. So just to summarize a few things about what we went over today. So, you should usually think of a computing system as having 4 main elements: the processor, primary memory, I/O devices, and some sort of a bus or interconnect that provides communication between the devices in the computing system. It's important to understand the fundamental way that a computer works at the hardware level, right? So it operates by performing many instruction cycles per second. These instruction cycles are very simple. So the kinds of instructions that can be supported by a computing system are simple arithmetic: add 2 numbers together, subtract some numbers, do multiplication, or simple sort of Boolean operations, so do like a AND of 2-bit patterns or an OR of 2-bit patterns, that kind of stuff. So that's most of what happens for the data processing kind of instructions, okay? So the power from a computing system comes from being able to do lots of those really fast every second, all right? So at the fundamental level, a computer is just always repeating the same steps. It fetches the next instruction according to what the program counter is pointing to, and then it decodes and executes that instruction, right? And then it just keeps doing that. Fetches the next instruction, executes, and so on. All right. So that's it for this video, and I hope that will help you with your assignment, and I hope to see you again later on.